Now let's analyze the variable flow processes. Now many processes like filling up of a tank or evacuating of a tank are not steady, and such processes can be analyzed by the control volume technique. So we will be making use of the control volume technique. Now to understand this, let us consider this diagram which shows that a device is handling a fluid which is flowing under non-steady conditions. Okay, so this is the control volume and this is the control surface, and these are two sections, section 1 and section 2, right? And the two things that we are interested while analyzing a non-steady state flow is, or a non-steady state operation, is that we need to take care of the rate of accumulation of mass within the control volume and the rate of energy accumulation within the control volume, right? So if you look at the rate of accumulation of mass within the control volume, this is equal to the net rate of mass flow across the control surface. So net rate means that the mass, sum of the mass flow rate which is coming in, and if you subtract the mass rate which is going out, that would be the rate of mass accumulation. So m1 dot minus m2 dot will give you the rate of accumulation of mass within the control volume, and this is dm1 by dt minus dm2 by dt, and this is equal to dmv by dt, where this mv is the mass of fluid within the control volume at any instant. So this is the mass within the control volume that is accumulated inside the control volume, right? So this is the first thing that we are interested in because it is a non-steady state condition. The next thing that we are interested in analyzing is the rate of energy accumulation. Now the rate of energy accumulation within the control volume is equal to the net rate of energy flow across the control surface, and that is equal to rate of energy inflow, all right, minus the rate of energy outflow. All right, now let's start with the rate of energy inflow, and this is equal to the rate of energy accumulation within the control volume. Now the energy accumulated in the control volume at any instant, let us say that is EV, and EV is equal to the sum of residual energy plus the kinetic energy, that is mv square by 2, plus the potential energy. So this is the energy which is accumulated in the control volume at any instant of time. Okay, and the rate of change is dEV by dt, which is d by dt of all this u plus mv square by 2 plus mg into z. All right. Now if you draw one more diagram that shows an unsteady system, so let's draw it. So this is the unsteady system. Okay, let's draw the control surface. So this is the control surface. Okay, let us mark it. So this is control surface and this is the control volume. You have two sections. The inlet section is section 1 and the section of outlet is section 2. Now let's put in the values over here. So the energy or the rate of energy which is coming in to this unsteady system is m1 dot into h1 plus v1 square by 2 plus Gz or Gz1. Along with it, we'll have some heat influx as well. So the rate of heat influx is d dash q by dt. Now you will have some work outflow, which is, let us say, some shaft work, which is dwx by dt, and some heat outflow, which is m2 dot into h2 plus v2 square by 2 plus z2 into g. So this is the energy outflow. Now this plus this is the total energy inflow, and this plus this is the total energy outflow, the rate of total energy outflow, and whatever that is left in the control volume is this. So you will have d by dt of u plus mv square by 2 plus mgz v. So this is the rate of energy accumulated within the control volume. Okay, so if you write down this as an equation, the rate of energy accumulated in the control volume is this, and this is equal to the rate of energy inflow, which is this quantity plus this quantity, which is m1 dot into h1 plus v1 square by 2 plus z1g plus d dash q by dt minus the rate of energy outflow, which is the sum of this plus this quantity. So you'll have m2 dot into h2 plus v2 square by 2 plus z2g minus dwx by dt. Now this equation, this whole equation, is what we call the general energy equation. So we'll give it a name, and this name is the general energy equation. Energy equation. And this can be used to analyze an unsteady system or an unsteady flow condition. Now, two special conditions. If the condition of the system is a steady system, if the system is steady. For a steady operation, the rate of energy accumulation is 0. So you'll have dEV by dt is equal to 0. So when this thing becomes 0, the general energy equation becomes nothing but your steady flow energy equation. So this is a point worth remembering. So for a steady flow operation, the general energy equation, that is this, becomes steady flow energy equation. Next sub point is, if we consider a closed system. Okay, for a closed system, so there is no mass inflow or outflow. This means that m1 dot is equal to 0 and m2 dot is equal to 0 as well. So when these two things are 0, then the equation reduces to, it should not be dash, so dEV by dt is equal to d dash q by dt minus d dash wx by dt. So I hope by now you understand why do we put a dash on top of d for q and w and not for e, because of the difference between path and point functions. Now this can be further written as dEV is equal to d dash q minus d dash wx. So this is nothing but your first law of thermodynamics, or d dash q is equal to d dash wx plus dEV. So this is actually the definition of your first law of thermodynamics. So this means that if you have to analyze an unsteady system, which is a closed system, you can straight away apply the first law of thermodynamics. But if you have to apply an unsteady open system, then you have to use the general energy equation. So this was the analysis of a variable flow process. Now in the next video, let's have a look at some example of a variable flow problem.